So why do we care about these summations? Why do we care about this? Well, we are going to start trying to find the area beneath the curve. We're going to estimate it using shapes we do know, because this is a shape. For instance, here it says, consider the region bounded by the graph of the y-axis, the curve of f of x equals negative x squared plus 25 on the interval negative 1 to 5. So this is the area, and we want to find the area of that shaded region. Well, that's a shape that we don't know. We don't have a formula for the shape of that. So what's our estimation? What we can do is we can make a bunch of rectangles underneath that estimate it. And you can see some of the rectangles are going to overestimate, and then in other areas we underestimate. And the idea is, hopefully when we add these together, we get a nice estimation of the area. But what are we doing? We're summing the area of each of these rectangles. So we're going to be adding a lot of things together. So I'm just picturing in my mind here, when I think about it, I have the sum of I equals 1 to, well, let's count here. 1, 2, 3, 4, 5, 6 rectangles. 6 rectangles. And then here I'm just going to say A sub I, where A sub I is the area of the ith rectangle. So this would be, if you look at this, I'm talking, this would be A sub 1, A sub 2, A sub 3, right? A sub 4, A sub 5, and A sub 6 would be that area right there. So that's what I'm talking about, is we want to use this summation notation to start looking at a way of quickly writing the area of the rectangles beneath the curve. And this is only 6 rectangles. 6 rectangles is something we could do by hand, but let's think about the previous problem. How many quote-unquote rectangles did we do on the previous problem? We did 1,000, right? So there's no way that I'm going to add 1,000 of these things together. And what if I wanted to do 10,000 or a billion or a trillion or even more than that? What would happen? Well, I'd be looking at the limit as the number of rectangles approached infinity. And as we saw in the previous problem, sometimes that converges to an actual number. And that number would be the exact area beneath the curve. So that's a big picture of what we're doing. We're adding together rectangles. When it's a small number, we can find the area of those rectangles by hand. When it gets to a large number, we're going to have to revert back to this summation notation that we used on the previous page. We're going to have to revert back to the formulas that we learned on the previous page. So it might seem like we're stepping completely away from what we did, but there is going to be a link. We just need to do it in baby steps. So let's read through this again. The idea is we want to find the area beneath the curve of negative x squared plus 25 on this interval negative 1 to 5. I'm telling you, it is not written in the books like this. The book does it a little bit differently. It talks about finding the area beneath it, or finding the area of different shapes. So you are going to have some different numbers in the book than you do in this example. So I tried to clean it up for you and make it as nice as possible for you. They do have a very similar function. They do have negative x squared plus 5, but they use the x values from 0 to 2, which gives us a lot of fractions, a lot of decimals, and I didn't want to do that to you. Okay? So let's take a look at this. It says we wish to approximate the shaded region. To do this, we will use the shapes that we know the area of, such as rectangles. To estimate the area in the bounded regions, we would determine the area of each rectangle and then add the areas of these rectangles together. So we already talked about that. So how are we going to estimate the area? Now, this is not exactly how they do it on the book, so I need you to read this and understand this. Very, very, very important that you look at this, okay? What are you going to do? Well, if you want to estimate the area on a closed interval, so here I'm going to call this point A and I'm going to call this point B, okay? So on the interval from A to B, the first thing you need to know is you want to know how many rectangles do they care about, right? How many rectangles do they care about? We're going to call that number n. So in this case, we had 6 rectangles, right? The second thing you need to do is you want to determine the width of each rectangle. We call the width of the rectangle, we're going to call the width of the rectangle delta x, the change in x, right? So let me go back up here. The number of rectangles is called n, the width is delta x. So what are we going to assume? Well, the height of all these rectangles is different, but the one thing we want to make consistent is the width is always the same. So how do we make sure the width is always the same? Take the total distance. In this case, it was from -1 to 5, and the distance between that would be 5 minus -1, so that's 6. So subtract your endpoints, 5 minus -1 would be 6, and then divide it by the number of rectangles. So in this case, we wanted 6 rectangles. We had 5 minus -1 was 6, divided by 6. That means the width of every rectangle, delta x, would be equal to 1. And if you notice, every single one of these rectangles has a width of 1. So in general, how do you find the width of the rectangles? The right endpoint minus the left endpoint divided by however many there are. It's really just an average. Okay? So the third thing, what are you going to do once you do that? Well, I want you to draw that interval, and I want you to break it into those rectangles. Again here, let's consider this situation in the picture above. So in the picture above, we have n equals 6 rectangles is what we wanted. For the width of a rectangle, we would subtract the endpoints. So that would be 5 minus -1 all over 6. Those are my 2 endpoints in the pictures. And that would be 6 over 6, which is equal to 1. So the width of every rectangle is 1. So there's my first step. There's my second step. The third step says what you're going to do is you're going to draw the interval. So let's draw the interval here. Start at the left endpoint, end at the right endpoint. So that was -1 to 5. We need to break it into that number of rectangles. So 6 rectangles. So I need 5. 1, 2, 3, 4, 5. Try to make them spaced as equally as you can. And then the idea is start from the left endpoint and just add whatever delta x is every single time. So delta x is 1. So this would be -1, 0, 1, 2, 3, 4, and then 5. So if you notice, like my first rectangle, the area would be right there. Second rectangle would be right there. Third one, fourth one, fifth one. I have most definitely 6 rectangles that I've created, okay? So that's step 3. Number 4 says circle the endpoints that you wish to use. So we need to determine the height of each rectangle. The height of each rectangle. So to determine the height of the rectangle, usually what I'm going to do is choose some point. So for instance, here's the first rectangle. How did I determine the height of that rectangle? Here's the second rectangle. How did I determine the height of it? Well, usually what you use is either the left endpoints to do it, or the right endpoints, or sometimes you even use the middle of each one of these points, okay? So it totally depends on what the problem wants. Sometimes you're going to use the left endpoint of the rectangle to determine the height, the right endpoint, sometimes the middle, sometimes somewhere else, okay? And then number 5, if you know the height of it, which you just determined by plugging in the function value, either the left endpoints or the right endpoints, you're going to use the function value. You know the height, that's the function value at that point. You know the width, that's delta x, so you can find the area. So how do you find the area? Well, it's a rectangle, so you're going to do the height times the width. You know the height, you know the width. So you can find the area of each one of those rectangles by multiplying the height times the width. That's step 6. And then number 7, you find the total by adding them all together. So those are our stages right there. Determine how many rectangles, find the width of each rectangle, draw that number line to break it up, determine which points you use for the height, find the function values which determine the height at each one. You know the height, you know the width, so you can find the area of each rectangle, and then you're going to add them together. I know that's a lot of steps, so let's see it in action in the next few problems.